The work I'm going to present is titled AccelWord, Energy Efficient Hotword Detection through Accelerometer. So the work was done by Li Zhang, myself, Mulchen Wu, Yishin Zhao, and Prashant Mohapatra at UC Davis. So here's the problem, and here's the solution in a nutshell. So the problem that we are dealing with is that current voice control applications are actually more energy efficient than what ought to be. And the main cause why they are energy expensive is that because they have to continuously listen for the hot words. And the solution that we are proposing is that we can use the low power accelerometer to listen for the audio signals, and you can use the same accelerometer to actually perform the hotword detection, and that way the overall approach is going to be much more energy efficient. So why we need to worry about the voice control? So the voice control applications are very popular right now on smartphones. So we all use Google Now, Apple Siri kind of applications where you can interact with the device using the voice control given to the smartphone. Similarly, they are a primary way of communicating with the wearable devices, because they have a very small real estate to actually perform any touch gestures. So smart glass, smart watches kind of things, they are primarily using voice control as the way of interaction. Similarly, there will be a lot of future devices which are likely to be surrounding us, smart devices that are low cost, low power, and they will be also using voice control as the primary way of interacting with the device. And Amazon Echo Speaker is a good example of such kind of device where you can interact with the speaker using hot words like "Hi Alexa." So how do the current voice control applications work? What they do is they typically constantly listen for a specific hot word. So this hot word can be "Okay Google" or "Hi Galaxy" or "Hi Siri." And the moment they can actually detect this kind of hot word from the user, they will actually start the voice control application, and the voice control application will then listen for the exact command that is given by the user. So you'll notice that this involves a continuous audio listening. That means the microphone has to be continuously on in order to listen for the hot word from the user. So we actually do an experiment where we measure the voice control on the power energy consumption for the voice control application for two voice control applications, Google Now and Samsung S Voice. And we compare that with a third voice control application, which is simply a microphone, which is simply listening what user is saying, and that is the microphone application that is shown there. And we measure the power consumption for the two separate devices, Samsung Galaxy S4 and Nexus S. And we observe that the voice control applications actually consume substantially more energy compared to the microphone itself. So this is expected because they have to continuously listen for the hot word, and whatever is they have listened for, they have to compare it whether that is a hot word or not. And what we conclude is that this continuous listening for the hot word is a major factor of high power consumption of the voice control applications. So how would an ideal hotword detection scheme look like? So first of all, we would like to have a high accuracy in hotword detection. That means if the user speaks the hot word, we want to be able to detect the hot word with a very high accuracy. Otherwise, there will be a lot of annoyance to the user not being able to interact with the application. It should be robust to multiple factors. One is user mobility. It should work in the case where user is mobile. It should work with different voice frequency, male, female, gender difference should not be mattering. Same thing, it should work in different noisy surroundings. And one important, since it will be always listening for the hot word, it should be energy efficient. That means it should consume as less as possible for listening for the hot word. So in this work, what to address this challenge is what we propose is to use Accelerometer for listening for the spoken voice. So what we show is that there is an empirical evidence that the accelerometer signal, accelerometers are actually sensitive to the spoken voice. So whenever the user speaks any words, the signal strikes the accelerometer mass, and it registers a non-zero acceleration. So now what we propose is, can we actually listen using the accelerometer? If we can do that, that means accelerometer are actually very cheap sensors and they are very low energy as well. So, and all the devices, all the smart devices already have this sensor. So, can we then utilize accelerometer for the hotword detection? So, for this we do a feasibility study. What we do, so the figure on the right top is we have a speaker phone and a receiver phone. The speaker phone plays user's voice continuously, and the receiver phone at the bottom registers, just records the accelerometer signals. And what you observe is we play the sound such as user speaking vowel A continuously, male as well as female, and we observe at different sound pressure levels. So sound pressure level is sort of an absolute measure of how loud the voice is. And what we observe on the right two bottom figures is that this, whenever we play the sound, there is a non-zero acceleration observed in multiple axes of the accelerometer. And this is true for both male and female, with the female being higher frequency. And as the sound pressure level increases, we are actually observing more and more acceleration. So that means it is similar to recognizing voice, where you have a higher, louder voice actually registering more amplitude. So, the question then is, can we use the accelerometer to listen for the hot words? We keep on saying that the accelerometer is actually a low energy sensor, but how low energy it is compared to the gyroscope and microphone. So for that we perform experiments for recording accelerometer, gyroscope and microphone for 6 hours and 12 hours continuously, and we observe that accelerometer is actually comparatively much less energy consuming compared to even gyroscope, and much less than the microphone itself. So if we are able to actually recognize the hot words using accelerometer, that means we will have a good amount of energy saving. So what are the challenges in terms of, so if we want to perform the hot word recognition using the accelerometer, what are the challenges? What are the problems that we will face? So first thing is that the user voice is a signal from 20 Hertz to 22 kilohertz, which is striking the accelerometer, and most of the current operating systems allow us to only sample the accelerometer at 200 Hertz. So that means the signal that the voice signal that is received by the accelerometer is going to be much low quality. So how do we do the hot word recognition in such case? The other thing is human mobility, which is that an accelerometer will also be affected by when the user moves. So how do we distinguish between what is the voice signal and what is the mobility signal? Similarly, how well it will perform in the case of when there is a lot of noise around the user. Okay, so there are multiple ways of actually recognizing the sound itself in literature, and we can use any voice recognition features to perform the hot word recognition. But since the signal is only 200 Hertz received on the accelerometer, we will not be able to actually apply any just generic voice recognition technique to perform the word recognition. So what we do is we apply the generic activity recognition features, which are used for detecting walking, running, and these features are time and frequency domain features. And what we show at the bottom is we measure the information gain of how good or how bad these features are in terms of recognizing whether whatever is spoken is actually a hot word or not a hot word. So we are just doing a binary classification here, which is whether it is a hot word or not. So the next question is, how do we combat the mobility interference? That means if the user is moving as well as actually providing the hot word input, how can we distinguish between the two? So we know from the activity recognition literature that the human's activities are actually concentrated on much lower frequencies. So at the bottom there are two figures. On the left one we have static user, where the user speaks to OK Google and good morning, 2 sentences, and what is the registered frequency domain signal on the accelerometer. On the right one we have the same while the user is mobile or user is walking. And what you observe is that in the mobile case, in the lower frequency, less than 20 Hertz or 30 Hertz, we are actually observing much higher energy in that frequency band. That means the user's activity is concentrated in that energy band. So this is good. This means we can actually apply a high-pass filter to remove the low frequency noise which is caused by the human mobility and keep the signal that is impacted by the voice. but how to choose the actual cutoff frequency for the high pass filter. And because if we choose a frequency that is the cutoff frequency that is too low, then what will happen is it might not actually remove sufficient mobility interference. If it is too high, then it might actually remove the voice input signal that is recorded by the accelerometer. So we do an empirical study again to measure the information gain of frequency domain features and at different cutoff frequencies. So at the bottom we show 3 frequency domain features and we analyze their information gain. We observe that around 2 Hz is where we actually achieve the maximum information gain. That means at that point we are able to achieve the balance between removing the mobility interference while keeping the actual impact of the voice control. After that, we will be actually losing a lot of signal that is impacted because of the voice. Okay, so we built the AccelWord Classifier on an Android device. We use 2 Android devices, and we apply a sliding window approach where we save the 2-second signals of the accelerometer and keep on checking whether in that 2 seconds whether hotword was detected or not, and using a simple decision tree classifier. And we build 1 classifier per user, so that is 1 classifier is trained per 1 user. And the experiments were done with 10 volunteers with 5 females, 5 males. Each of the user is asked to pronounce 10 hot words, 5 in mobile cases, 5 in stationary cases, and 20 random sentences, which are any short sentences such as good morning, how are you, and things like that. And what we do is then each of the 10 hot words and the 20 random sentences, we play them repeatedly 10 times with a different background noise for the training. And we compare the performance with Google Now or Samsung S Voice, which are the 2 applications which we could use on the Android phones, and compare the true positive rate, false positive rates, and energy consumption. So here's the results about the true positive rate for the hotword detection using the Accel Word. So what we observe is in this case we train and test with the same SPL level. So this means we are training at a given SPL, all the instances of a given SPL, and we are also testing with the same SPL level. What is observed is that the actual accuracy decreases as the SPL decreases. That means for a lower voice, the accelerometer has lower impact, and that is more difficult to actually it's difficult to observe. The false positive, but still for the SPL levels which are higher than 60 dB or 55 dB, the performance is still comparable with the current voice control application. I'll show the results for those as well. The false positive rate, on the other hand, is around 5% for most of the cases. Now we look at the results for cases where the testing and the training are happening at 2 different SPL levels. So that means that if the SPL is, and what we observe is that the models that are trained and tested with the same or higher SPL, they perform better. That means they achieve higher TP rates, and this is again same. The results are presented for both male and female, and we observe pretty much the same performance for both male and female. And the reason to consider the female is because female frequency is female voice frequency is observed to be much higher than the male voice frequency. And here's the result comparison with the Google Now and Samsung S Voice. So we observe that actually as the SPL decreases, applications like Google Now will drop the TP rate, the accuracy much faster. Even faster than Accel Word. So it stops detecting after a certain SPL, it stops detecting the OK Google or this kind of word inputs. On the other hand, Accel Word still can detect this hot words. Similar the results were observed for the Samsung S Voice. So But what we can compare here is that the AccelWord for different SPL level is still incomparable, achieves still comparable performance with the Google Now and Samsung S Voice. This means we can actually use the Accelerometer for listening for the hot words. In this experiment, we show what is the impact on hotword detection accuracy in presence of the background noise. So we play random background videos and actually create the different SPL levels of the background noise, and again perform the comparisons between AccelWord, Google Now and Samsung S Voice. What we observe is actually as the background audio SPL increases, AccelWord performs worse compared to the Google Now and Samsung S Voice. That means in the presence of background noise, our technique performs worse compared to the two Google Now and Samsung S Voice. And the reason is expected because the current so Google Now and Samsung S Voice utilize this microphone, and they have already good techniques to cancel the noise for the microphones, both in hardware and as well as in software. So this is expected given we don't have any good noise cancellation technique in AccelWord, that our performance in the presence of background noises is not comparable. So then we perform the experiments with the mobile scenario, where user puts the phone on, ties the phone on the wrist and walks at the usual walking speed indoors, and provides the voice input. And what we observe is that the 2 Hz filter, cutoff filter that we had chosen for removing the mobility interference works pretty well, even in terms of the comparison with the accuracy. So in the figure in the middle, what we observe is that as we change the filter cutoff frequency, at 2 Hz we achieve the maximum true positive rate for AccelWord. Beyond that, the accuracy actually drops substantially. That means we are actually removing the voice signal that is carried because of that is carried over the accelerometer, and without that it will be difficult to. So the 2 Hz choice of 2 Hz is what we think it is the correct choice for removing the mobility interference. Okay, so the last results about energy efficiency. This means that there are we perform so Google Now and Samsung S Voice. We do not know how periodically they actually check for the hot word, but we try out different intervals after which we check for whether there is a specific hot word or not. And in this one, we observe that as we increase the interval for calculating whether the last 2 seconds of data contains a hot word or not, as we increase that as expected, this is that the frequent recalculation decreases, and the energy consumption also decreases. So, and compared to the Google Now and Samsung S Voice, the total energy savings that we can achieve because of listening through the accelerometer is around 50% in most of the cases. So this means if we are able to actually observe the or listen for the voice signal using accelerometer, we are able to not only achieve a very high accuracy of hot word detection, but can actually save a lot of energy, around 50% compared to the current voice control applications. So there is an added advantage of using accelerometer for the hot word detection, and that is that we can actually perform speaker identification as well. So most of the current voice control applications do not allow this kind of speaker identification. This means when we are providing a voice command, can we actually also identify that who is the owner, whose voice it is? If that is the case, then we can my OK Google command will not affect anyone else's phone, or it will not take commands from any other user. So we check the performance between the 10 users and see how much is the how uniquely it can identify different users, how uniquely it can classify between them. And we observe that in terms of gender, it can clearly identify in all cases, it can clearly identify if the user is male or a female. Similarly, for speaker identification for female, 82% of the time we can say we can uniquely identify from the 5 users, that 5 female users we had, and similarly for male with 88% of the time. So this accelerometer, hotword detection using accelerometer has an added advantage of doing the speaker identification. Okay, so there are certain limitations of the work, and these are the directions for our future work. The first major limitation is noise cancellation. This means that if there is sufficient noise in the background, how do we actually cancel this noise? And we have to develop techniques to actually cancel this noise. Mobility patterns, which is we have tested for specific mobility patterns like walking, but if we want to deploy it for real mobility cases, we have to test it for other cases like driving in a car or running and this kind of things. And how do we actually remove the high frequency mobility noise? So this is one of the important directions of future work. There is another advantage of knowing that accelerometer can register the voice signal, and that is because most of the current applications for the accelerometer and applications that use accelerometer and gyroscope do not require any specific permissions to access the sensors. So this means that actually any application accessing the sensors can recognize your voice and listen for them, and this might be a big privacy concern. So how do we design protection mechanisms for this kind of things? Okay, so with that I conclude, and I'm happy to take any questions.